Okay, welcome back everyone. So this is the third video in the tutorial. At the end of the last video, we were talking about the fully permissionless setting without resource restrictions yet. Right, and we stated the proposition written here. Okay, so consider the fully permissionless setting without resource restrictions. And suppose that the player set is finite. For every row greater than 0, no protocol solves Byzantine agreement when up to a row fraction of the players may be Byzantine. And importantly, so this result holds even in the synchronous setting with a known player set and with all players active at all time slots. Okay, so as we said earlier on, okay, in moving from the permissions to the fully permissionless setting, we've introduced these three new complexities, right? You now have an unknown player set of unknown size, you have the possibility of players being active and maybe inactive at certain time slots, and there's also the possibility of sybil attacks. Okay, so it's really, here it's the possibility of sybil attacks that's driving this particular result. Okay, so what I want to do next then is just to go through the proof of this proposition. Okay, so I minimize myself so you can see the screen. Okay, so yeah, so we're going to give a proof for the deterministic case. Okay, actually the theorem there was stated for the deterministic case, but the argument extends easily to probabilistic protocols and the natural probabilistic version of Byzantine agreement as well. Okay. Yeah, so towards contradiction, suppose that such a protocol exists. Well, suppose delta equals 1. Choose n greater or equal to 3, such that 2 over n is less than rho. So remember that rho is our bound here on the fraction of the players that can be Byzantine. Okay, so if we suppose that 2 over n is less than rho, that just means we can corrupt up to 2 of the players, okay, and keep below our rho bound. Okay, so we're choosing n greater or equal to 3. Such that 2 over n is less than rho, and we consider a set of players p0 up to pn minus 1. Okay, and then we're going to let id1, id2 up to idn minus 1, and id1 prime, id2 prime up to idn minus 1 prime, denote two n minus 2 disjoint sets of identifiers. Okay, and then we're going to consider 3 possible executions of the given protocol, and it's going to be a simple indistinguishability argument. Okay, so as I say, we're going to consider 3 different executions. Okay. So this is our first one. So in the first execution, player P0 is Byzantine, and players P1 up to Pn minus 1 are honest. All players are active in all time slots. That's going to be true in all the executions. Okay, inactivity is going to be nothing to do with this proof. It doesn't play a role here. Okay, for each honest player, Pi, their identifier set is just IDI. Okay, so far so simple. For P0 though, the Byzantine player, we're going to let them control all of these identifiers here, the ID1 prime up to IDN minus 1 prime. All players receive an input of 0, so we immediately know that all the honest players have to terminate an output 0. How then does P0 behave? This is our Byzantine player. Well, P0 ignores its input and simulates the behavior, including messages sent, of n minus 1 honest and fictitious players P1 prime up to Pn minus 1 prime that all have an input of 1. With IDPI prime equals IDI prime. Okay. So the important thing, the most important thing to remember here is that all players in this execution receive an input of 0, so all the honest players have to terminate an output 0. Okay, and then we come to our second execution. Okay, in the second execution, the basic idea is we want to ensure that the second execution E2 is indistinguishable from E1 as far as P1 is concerned. And that's our main aim here. Okay, so in E2, again, player P0 is Byzantine and P1 up to Pn minus 1 are honest. Okay, again, as in all the executions, all players are active in all time slots. Right, we want to make sure, as I said, we want to make sure this execution is indistinguishable from E1 as far as P1 is concerned. So for P1, well, I'll leave their identifiers at the same. So ID P1 is just ID1, as it was before. For every other honest player, though, every other honest player PI, IDPI is now IDI prime, right? Those identifier sets were controlled by the Byzantine player P0 previously. Okay, again, we want this to be indistinguishable from E1 for P1. So player P1 receives again an input of 0, but all other honest players now receive an input of 1. Okay, and P0 now, they control, so ID P0 is ID1 prime, they controlled that set before, but now it also controls ID2 up to IDN minus 1. Okay, these identifier sets were previously controlled by P2 up to Pn minus 1 in execution E1. And what P0 does is it just simulates n minus 1 honest players, P1 prime up to Pn minus 1 prime, under the conditions that P1 prime has an input of 1, and P2 prime up to Pn minus 1 prime each have an input of 0. ID P1 prime equals ID 1 prime, and ID Pi prime equals IDI for I is 2 up to n minus 1. Okay, so the important point here, as I say, is that in this execution, things are indistinguishable from execution E1 as far as P1 is concerned. Okay, now P1 outputted 0 in execution E1. That means they have to output 0 in this execution, which means all honest players still have to output 0. Okay, then we move to our third execution. Okay, and the idea here is that we're going to make sure this execution is indistinguishable from E2 as far as P2 up to Pn minus 1 are concerned. Okay, so they still have to give the output of 0. Okay, so in this execution, so P0 and P1 are now Byzantine. Remember, we're allowed to corrupt up to 2 players. And now P2 up to Pn minus 1 are honest. Yeah, I mean, we want to make sure the execution is indistinguishable from the last one as far as these guys are concerned. Okay, again, all players are active in all time slots. All players now receive an input of 1. Okay, remember P2 up to Pn minus 1 received an input of 1 in the last execution, while P1 received an input of 0. Okay, so far this is indistinguishable from the previous execution as far as these guys are concerned. Okay, identifier assignments for all players are the same as in the previous execution, E2. Okay, and P0 and P1 behave identically as in execution E2. So in particular, P1 acts as its input as 0. Okay, so the point here is that we've made sure here that this execution is indistinguishable from E2 as far as these guys are concerned. They had to output 0 in the previous execution, so they still have to output 0, but now all players have an input of 1. Okay, so they all actually also have to output terminate and output 1. So that gives us our contradiction. So summing up then, okay, so the following observations complete the contradiction. So by validity and termination, in E1, all players must eventually output 0. Okay, they'll have input 0, so they have to output 0. Similarly, by validity and termination, in E3, all players must eventually output 1, because they all have output 1, input 1 there, sorry. Okay, but because the executions E1 and E2 are indistinguishable for P1, P1 must eventually output 0 in E2. Yeah. And by agreement and termination in E2, all honest players must eventually output 0. And then last we reach the contradiction. Because the executions E2 and E3 are indistinguishable for all the players P2 up to Pn minus 1, they must output the same value in both executions, which means they have to output 0 and they have to output 1 as well. Okay, so we reach our contradiction. Okay, again, we have to repeat. It's really the possibility of sybils that drives this proof. Right, the proof goes through. It works perfectly well with a known player set of known size, and when we assume that all players are active at all time slots. Okay, so this proposition shows then that to make progress in order to make consensus possible, somehow bound the combined power of Byzantine players, and in a way different from the traditional approach of bounding the fraction of players that are Byzantine. So how should we phrase such a bound? Well, the proof of the proposition fundamentally depends on the ability of Byzantine players to costlessly generate an arbitrarily large number of sybils, which in turn enables the simultaneous simulation of an arbitrarily large number of honest players. The bound must therefore concern something that is scarce and costly to acquire, something that prevents a Byzantine player from carrying out a simulation of many honest players. Okay, so these ideas bring us to the notion of resources. Right, we've motivated the introduction of resources. Okay, so in the next video, what we'll do is we'll start talking about how we're going to model, how we'll model resources. Okay, so I'll see you there.